Um, okay. This session is going to be revision for paper 3 for your applied, so your stats and mechanics, the final ever paper for maths. Great. Um, and with the thing is with stats and mechanics, obviously you've not done stats and mechanics. Unlike what I mean is. Maths obviously had paper 1 and paper 2, but by paper 2, we could have guessed on the topics and what could come up. The thing is with stats and mechanics, everything will come up. And so I think the best way to revise is actually doing past papers, I think. And this is and what we're going to go over is the June 2022 paper for both stats and mechanics today. As for again predicting topics, obviously paper 2 was very very iffy. A lot of topics didn't come up. Now actually that doesn't mean that, for example, binomial expansion or whatever could come up in paper 3, because it's a really dodgy situation essentially. Because I think there were meant that the paper you sat in paper 2 wasn't the paper. I think it was a backup based on what I've seen online. Uh, and so I think the exam board might have messed. I don't know, but I think the paper 2 wasn't intended anyway, so I don't think you can kind of use that to kind of predict what happened in paper 3. So I think the best thing again is just doing past papers. And the questions are pretty much the same, especially with mechanics. And so yeah, I think the best way to go over is past paper. So this is June 2022. We're going to start with stats. And yeah, and also I'll try to get this calculator on here. Hopefully you can see. So you can see what to input as well. And also this is not. This will be the class whiz. I don't have the fancier calculator, so this should be applicable to everyone. What I'm going to go over. So stuff like accessing, like your binomial distribution, your normal, calculating probabilities, and all that sort of stuff. I'll show how to do it with like the normal calculator, so everyone should benefit from it. Anyway, I'm gonna stop waffling. Look at this question then. So we are told George throws the ball at a target 15 times. So numbers are going to be important here, obviously. Each time George throws the ball, the probability is 0.48. The random variable represents the number of times George hits the target in 15 throws. Part A, find the probability that x equals 3. Okay, well, obviously we're going to have to use some sort of distribution here. I think clearly we're going to use the binomial one, right? Because it's discrete data. Because we're looking at how many times he hits the target. Obviously, that's going to be like a discrete number, an actual integer, right? So it's going to be a binomial, and so every binomial obviously is in the form n of p, where n's the number of trials and p is the probability that you want. Okay. Well, in this case, we have 15 throws, so n is 15, and the probability we're interested in is him hitting the target, so it's going to be 0.48. Okay, and that's what we highlighted there. So actually, then using this distribution, then we can work out probability x equals 3, and that's going to be calculator work. So let's see if we can get this working. So with this sort of calculator, you're going to want to go on the menu, go to option 7, and then you're going to want the binomial PD. I know CD means cumulative, but I actually can't for the life of me remember what PD means. I don't know, but essentially it gives you the probability of a certain number, not a range of numbers, but just a number. So we're going to click 4 for PD. I guess I remember it as like particular distribution. I guess so like a particular value of x. I don't know. I don't know what it stands for. You're going to want variable, and then you got this menu here. So x is going to be 3. N Cool. N is going to be 15 and your probability is 0.48. And so we get this number here, 0.01966. And yeah, it doesn't say to round or anything. But you know, you can just give it to like 4 decimal places or something like that. They're not too fussy with the rounding or anything like that. And then for part 2, it says probability x greater than or equal to 5. Now, I don't know about the graphical calculator, but this one, the cumulative one, which obviously is like all the x values up to that point, the cumulative function on the calculator only works for values less than a particular number, not greater than. Well, here we have greater than or equal to 5. So the way we're gonna deal with that is, well, we want x greater than or equal to 5. Imagine almost like a normal distribution curve. So imagine we have this sort of curve here. I don't know. We have x is 5. Say here. I don't know. Obviously, we want all that probability here. But again, like a normal distribution, the probability, the total probability under the curve, if you will, has to add up to 1. So alternatively, what we could say is this is the same as 1 minus probability x is less than 5. Okay. So if it greater than or equal to 5, we can do less than 5. 1 minus when it's less than. Okay. But again, with binomial, it only goes in discrete numbers, so it goes from 1 to, well, I guess 0 maybe. 0, 1, 2, 3, 4, 5. Da, 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 da. Um, so if we want the number less than 5, it's going to be 4, isn't it? So x less than equal to 4. And the other thing to note is when you use a cumulative, it's particularly px less than or equal to a number, okay? Not less than, but less than or equal to. That is the key thing when you use a calculator like this. That's a probability. Every probability needs to be rearranged to this, pretty much. At least with binomial. And so then we need to work out probability x is less than or equal to 4. So that's going to be your cumulative function on your calculator. So if we go to menu again, oh god, go to 7. Then you want to scroll down to binomial CD, which is your cumulative. So it's for all the values less than or equal to. Okay, so it's adding them all up. And so obviously value is going to be 4 here. Again, the same Norton number of trials and probability. You get this. So 1 minus 0.079 868. Okay, blah blah blah. And so yeah, then you do that. Then you do that on like on the calculator again. So 1 minus 0. And the best way you can do that is actually look at what I'm going to do here. I'm going to say ons store as A, for example. Okay. So now when I access A, which is because it's red, it's going to be alpha. Click the alpha button to turn it into the red mode, and then you get the red option. And so then if I go back to the normal setting, if I do 1 minus A, so go to shift and then A here, you get the 1 minus that probability. So A was obviously that 0.079 that's stored in the calculator. So then I get 0.92 0131. Da, 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 da. And yeah, cool. Okay. Then it says George now throws the ball at the target 250 times. So now we're changing the number of trials to 250. Use the normal approximation to calculate probability. It'd be more than 110 times. So again, ultimately now, N is now, what was it, 260, was it? 250, oh, okay. 250, again, the probabilities are the same, that's 0.48. And, well, we want the probability that X, what was it, is the number of hits is more than 110, okay? However, it says to approximate this using a normal distribution. So what happens is, well, if we have another normal distribution of y, we're going to want mu and sigma squared, right? Uh, um, but how do we work out this mu and sigma? Well, I believe it's in the formula, but when you are approximating the binomial to a normal, so again, what will happen is as well, just to explain a little bit, like there's this graph here, when you have loads and loads of different datas, loads of values. So say for example, if we had this point here, I don't know, and we have the curve here. We have one probability here, and then another one here, then another one here, and another one here, another one there. But then if we add more probabilities, we can essentially convert the binomial to a normal because it starts to take a normal shape if you have more value. Anyway, you don't really need to know that. But how do we approximate? I believe it might be in the formula book actually, but I do know what it should be anyway. Uh, um, Here it is. It's this here. But they're called different things. Here. But they don't call it a normal approximation. But if we look at this section here, the mean, obviously that's your mu. If you then convert a binomial, the mean, which is the normal version, right? The normal approximation, which is the mean of the normal approximation, that's NP. Okay, so that's your number of trials. Oh, hang on a second. Okay. So the mean, then, as we saw in the formula book, it goes to NP. Now N is 250 and P is 0.48. So then that's going to be 250 times 0.48, 120. Okay, so that's your mu. Then your variance, no, your standard deviation sigma, is again, if you look in the formula book, it's here. It's going to be NP. So that's the mean times 1 minus P. Okay. So if we do that, that was the variance, so wasn't it? So the variance is standard deviation squared, so that'd be sigma squared. And then if you compute that, well, NP, we already worked out 120, and 1 minus P would be 1 minus 0.48. So that would be, if you put that in your calculator, 62.4. So then, therefore, then the normal approximation, the normal version of the binomial y, is now n of the mean 120, and sigma, the variance sigma squared is 62.4. Okay, so therefore then, the probability of the original x in the binomial world being greater than 110, so that's the probability hits more than 110 shots. Um, well, in the normal world with y, so p of y, well, probably again think it'd be greater than 110. However, what we then need, whenever we use a normal distribution, but well, approximation from a binomial to a normal, because we're going from discrete data to continuous data, we need to apply a continuity correction. The whole idea behind that is because of the fact that there's discrete and continuity going on, discrete and continuous. So probability x less greater than 110. Well, actually, because it's discrete, we've kind of rounded it. So we have 110 here. Then the lower bound would be 109.5, and the upper bound would be 100 and what's it, 110.5. Yes. Okay. So actually, well, actually, my apologies. Before we do that, no, that's not how we use the binomial. We need it to be greater than or equal to. So that will be the same probability that x is greater than or equal to 111. Okay. Then we need to apply the continuity correction on that. Okay. So it then 111. Then the lower bound 110.5, and the upper be 111.5. Then probability of y. Well, actually, we want the lower bound, right? So the lowest value that 100 that this x could be. So then y would be greater than or equal to 110.5. Okay. Um. So that's a continuity correction. Essentially, kind of like take like what's it called? Do like take the decimal part, so 110.5 instead of the okay. So that comes from the bounds, so the rounding. Because of the fact 110, when we do binomial, we can only take the nearest integer, right? Because it's by discrete, it's a whole number. But the continuous factors in for all the decimal parts in between. So to factor that in, well, actually, so the lowest value here of y would actually be the lower bound of decimal, because it can be a decimal, right? Because it's continuous data. But here, x can only be at the lower bound for x is 111 in the binomial discrete world. So then the lower bound for y, the smallest y, would then be the lower bound in the you know what I mean? Hopefully, you just need to understand you need to apply that every time, or you make a normal approximation. Okay, now we can just compute this probability. Because now we have all we have the normal distribution, right? We have your mu, your sigma, you have your probability. So let's work with that. So if it is 7, and then because we're normal, cumulative. Let's do 2. You never want normal PD, really. So normal cumulative, and this one you don't have to worry about really. Unlike the binomial, we have to flip. It can only be less than or equal to. Here, because it has an upper and a lower, so you can do any probability we want really. So again, the lower bound for y is 110.5. The upper can in theory be infinity, right? It can go from 110.5 to any number, above. So the way we can kind of write down infinity, if you will, is again give a very large number. So let's say 10 to the 100. Okay, there we go. Oh, got a math error. Yeah, math error because it didn't define the. There we go. Oh, math error. I thought. Is it too big for the cal? Oh, it might be too big for the calculator potentially. Yeah, there. Yeah, okay. Okay. So just do 10 to the 50, because obviously that's 10 with like 50 zeros, something like that. So it's a huge, huge number. Obviously, don't make it like I did too huge. The calculator can't work with it, because the calculator cannot work with large values like that. Anyway, 10 to the 50. Keep it simple. Then sigma, again, the sigma, the variant, well, the sigma is going to be square root 62.4. So where's the root function? Because it's sigma, not sigma squared. So remember that, 62.4. There, and it'll calculate it for us. Then mu would be 120. Uh, and so the probability we get is this. 0.88 543. Okay. Dot dot dot. And that is a 5. There we are. Cool. So again, you don't. You actually, when you convert to normal, if you can interpret this in the formula book, you don't have to learn the mean and the variance. And the variance, remember, is standard deviation squared. You don't need to remember what that goes to, although it's not too bad, I guess. When you go from a binomial to a normal, it gives it here. As long as you know what this means, it's in the formula book here. But yeah. But so really the only tricky thing there really, and I did get stumped a little bit on it, is to recognise this continuity correction. But yeah, that's whenever you do a normal approximation. Okay, cool, not too bad for question one. Question two. So we are told the length of a metal rod is normally distributed with a mean of A and standard deviation of X. So the proportion of metal rods less than 7.902 is 2.5%. That's going to be 0.025 as a decimal, right? A percent is times by 100, so divide by 100 to get the decimal, right? Show that x is 0.05. Okay, so it's kind of asking for the inverse, right? Because normally we put in the standard deviation, obviously, to get a probability. But this time we're given a probability and we need to work backwards to get the standard. Now, obviously, the calculator itself won't give you a standard deviation. It has an inverse function, but that's when you want to find the x value, which gives a particular probability. But the calculator cannot find a missing standard deviation. It will mean, it has to have those all the time. So the calculator won't immediately be helpful here. So how are we going to approach this then? Well, again, let's just write down the normal. What would it look like anyway? So again, we are given. Does it tell you what the variable is? L. Oh, there we go. So L will look like this. L will go to a normal of mean of 8, and the standard deviation is x. So it's going to be x squared. Okay. And we're also told that the probability of L, the length being less than 7.902 is equal to 0.025. Okay, cool. So we need to use this information to work backwards to get x. Okay. So what we're going to have to use here is actually something called the standard normal distribution, and this is a very particular normal distribution. Again, look at this, where the mean is at 0 in the middle, and the standard deviation, and therefore the variance would also be 1. Um, and that's helpful because then if we have a certain probability, and the idea is essentially when we have a certain probability, so 0.025, that, hang on a second. And oh, where's my pen gone? Where'd my pen go? Hang on a second. Okay, I found it. Sitting on it. Oh god. Okay, so the idea is with the standard normal, so that just means a normal distribution with these parameters. And mu is 0 and variance is 1. The idea is the probability will be the same for a particular z value. The probabilities of these two distributions, so here and here. Oh god, that's a horrible bell curve. There we go. And here, which is our actual distribution, so mean would be 8, and obviously the variance would be, well, x, the standard deviation. The idea is, again, the probability for L particularly will be the same. It will be 0.025, and the area here, we should denote the probability, will also be 0.025. But we need to work out this z value. And that's where the inverse normal function on your calculator will help, because now we know the probability for the standard, because we have the area, we have the probability, we have the mean and the variance. So the calculator likes that. So now we can work out and go reverse. If we know the probability, then we can work out the value, the number that gets us that, right, as z. So I'm going to say inverse normal with obviously the standard deviation for mu is 0, sigma is 1. So therefore, so I'm going to say probability then of z. What am I going to say? So mu 0 standard sigma is 1. So let's do that in the calculator then. I'll worry about what I'm going to write down after. So let's go to go back to 7. Now we're on the inverse normal, because I can know the probability. So the area is going to be 0.025. And with this, no, the area this time is like the binomial. It's only going to be less than or equal to the number. So for example, again, if I had, and again, the bell curve, but if I had this area instead, I'd have to do instead 1 minus the area before it, okay? Just like the binomial. But anyway, this time we do have less than, so that'd be fine. So the sigma would be 1, the mean would be 0, and we get this. So the inverse would give us the z value minus 1.595996. I guess I'll just write that down. I know what you mean by z. Z is like the variable associated with standard normal distribution anyway. I guess you could say that that probability of z. No, I'm going to leave it there. So that's our z value. So I'm really struggling what to write down here. I don't know why. Z is minus 0.9596. I'm going to say such that probability is less than 2.5% or something like that. I don't know. But okay, so now we have a z value. Again, now we can map from the normal to standard one to the actual one we have here, the bottom one. So then we can work out the so we can work with this. So what that's telling, well, actually, we know what L is here. Sorry, we do know what L is. L is 7.902. That comes from here. So actually, the only thing we're missing is sigma. But anyway, what you do need to know is when we can map from a standard normal to the actual normal we're working with, to two different curves, we can code it using this. So Z is, in this case, L minus mu over sigma. Yes. And that'll be for any normal distribution. But we know our z value. So in particular, we need the z and the L value that gives a probability under the curve. That's 0.025, right? But we know the z and the L value. We know that the z, as we just calculated, is minus 1.95996. And the L value is 7.902 minus the mean. Now that's the mean of the obviously of the original distribution. So that's going to be 8 over sigma. So then you're just solving for sigma. So therefore, minus 1.95996 sigma is 7.902 minus 8 would be minus 0.098. So therefore sigma then is going to be that 0.08 divided by minus 1.95996. Will get us 0.05. And actually, that's 0.050001. So I'm just going to leave it as 0.05. But yeah, so that's the whole idea, right? Is to realise when we have a missing sigma or a mean value, you're probably going to need to refer to the standard normal distribution. Then you can use your z value using your inverse normal function in your calculator to find the z value that gives the same probability under the curve as the original. And then you can use the coding formula, which is this, that goes between the standard and your actual normal distribution to work out any missing values. Okay, let me given that calculate the proportion amount of rods that are between 7.94 and 8.09. So that's just a simple probability. So we want the probability that 7 point, what was it? At 7.94. So and the length is between that and 8.09. Well, that's just going to refer to the calculator again. So now we know sigma. So we know that I should probably say x. Sorry, because x was standard deviation, wasn't it? So I'm going to say sigma equals x. Because remember, it was really weird in the question. The sigma x was 0.05. Um, Anyway, so now we know what sigma is. Again, to then find this probability, then go back to the normal CD. The lower region, now the lower value is 7.94. The upper is 8.09. The sigma is 0.05. And the mean was 8, wasn't it? So then we get a probability of 0.849. Okay. Cool. Okay. Okay, so then what's part C saying? So part C saying the cost of producing a single metal rod is 20p. A metal rod where L is less than 7.94. It's solved for scrap. We're given three regions of L essentially. Okay. Well, L's 7.94. The 7.94 to 8.09, and anything above 8.09. Calculate expected profit. Okay, and we're given the associated profit and cost of each region. Well, and we're given how many rods there are. So really, we kind of need to work out how many rods have a length of less than 7.94, between 7.94 and 8.09 and 8.09. So what we're going to need to do is, then obviously going to use the early parts of the question. We're going to need to work out the proportion of the rods that have those lengths. So that's what we're going to do. So then part C, before we do anything else, we need to work out these three probabilities. So the probability that L is less than 7.94, they've not told you that, have they? No, we have to work that out ourselves. So again, we have to go back to our calculator. Let's go back to our menu. There we are. So the lower, so it doesn't have a lower limit, it only has an upper limit this time. So the normal distribution actually goes from negative infinity to positive infinity. So actually, we need a low number of say minus 10 to the 50. Okay. So that'd be a big number, but make it negative. So it'd be a hugely negative number. So it'd be like negative infinity. Then the upper would be 7.94. And also bear in mind, I'll talk about that in a minute. And then the mean and the mean and the sigma will be the same. And you'd get this value here, 0.115. I'm going to leave it there because obviously it goes to 0, so I don't really mind, really. I'll leave it there. And what I was going to say is it doesn't matter with normal if you have less than or less than or equal to, or vice versa with greater than, because of the fact that it's continuous. So basically, at any point, probability that L is equal to some number K would always be 0, okay? Because of the fact there's just infinitely many points because it's continuous data. So it doesn't actually matter for that reason if you take less than or less than or equal to. Okay. It's kind of like saying they integrate with the same limit of like say like 2 and 2. Blah 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 blah. It will always equal 0 because of the fact you're taking away by the same limit. It's the same kind of concept. Anyway, so that's 0.05. Then we want the second bit. So probability of 0.74. 7.94, sorry. Less than L, less than equal to 8.09, was it? And actually, that was part B, wasn't it? That's our answer to part B. So it's 0.849. And so actually, at this point, you could say anything greater than 8.09 would be 1 minus the other two probabilities. But let's just work with the calculator practice. So then probability L is greater than 8.09. Again, you can use the calculator. And let's just go here. So the lower limit would be 8.09. The upper limit would be 10 to the 50, say a big number. So we get 0.0359. Okay. I'm going to leave that there. You could put a 3 if you want to. But yeah. There are also three significant figures, so I guess that's appropriate to do. And actually, if we were to add them all together, 0.115, add 0.849, add 0.0359, you get 0.999. Yeah, so it's basically 1. So we know we've done that right. But yeah, you could alternatively take one minus the other. But yeah, there we are. So we worked out the proportion of the rods. So I'm gonna say number of rods. L less than 7.94. So that's going to be the proportion is 0.115 of the amount we have. Well, the amounts we're dealing with here are 500 rods. So it's kind of like relative frequency. So it's going to be 500 and then 0.015 of that. So then that's going to be. Uh, I'm going to do. Uh, by the way, I'm doing these elementary calculations on the calculator off screen. It just makes it quicker. But I'll show the actual statistical stuff on the on the um on the screen. So 57.5. Okay. So I'm going to say that's equal to 58 because obviously kind of half a rod. And then the number of rods between 7.94 and we worked out that proportion with those two sizes 8.4, 0.849. There we are. Lots of 500. And again, that's going to be 424.5, and so that's going to go to 425 to nearest whole number or nearest integer. Um, and then lastly, the number of rods L, which is greater than 8.09. But that's going to be 500. Take away the other two, so 57.5. Well, well, it's going to be 58. Take away 425. So that'll be left with 17 rods. Okay, these one rods. They're all rods. Okay, so we've got 500, so 17 there. Okay. Okay. Trying to think, is there a cleaner way of doing this? Because there's a lot of rounding going on. I don't like this rounding. Hmm. No, I'll tell you what I'm going to do. I'm not going to round this, actually. I've already. I'm going to keep it as it is. These integers here, I'm going to leave it. I know we're kind of part of a rod. Um, but I'm going to leave that. Hang on a second. But I'm going to leave that there. Okay, I had to do something, and so I was off here for a little bit. Obviously I'll edit that out, so you won't see the break, the pause there. Yeah. So where we're off, I guess to recap. So we're finding the proportion of all the rods that had these lengths, right? These three various lengths here. So then we're computing the number of rods, so then we can work out how much profit and how much cost they give us. But we ran into a little bit of a problem with the rounding, and there's a lot of rounding going on. So now I'm saying, well, let's just leave it the actual answer. I know we kind of part of a rod, but that's not our final answer. Uh, so it's fine to leave it, intermediately. We just leave it as it is. So okay, then let's compute this bit. Then so 0.849 is 424.5, and so the L value would be five. The L value, the last value. Oh God. 500, and then it's subtract the other two. 57.5 minus 4.5 will get us, and actually that will be a whole number. But yeah, I'm not too worried about whole numbers at the moment. Get us 18. Okay, there we are. Okay, so we've got all these rods now. But we're also given the associated profit, the cost, and the how much they give us as well, like the revenue. So what we need to work out is, because we're asked for profit again, think back to paper one, no, paper two. To work out the profit, well, I think it's better to work out the total, the total amount you get. So how much we sell them for, right? Each rod. So the overall sales minus the cost, right, to get plus the profit. So how much we get minus how much we pay to make it. It's a bit of business there. Anyway, so then total sales then, as how much we get, right, is going to be how much we sell each rod for. So the first bunch of rods where the length is less than 7.94, we sell for 5p. Um, and I notice it's in pounds, so it would probably be best to convert this to 0.05 pounds. Same way we sell them for 50p, so it's 0.5. Okay. Uh, and then when L is greater than 8.09, it costs an extra 10p. We'll worry about that in a minute when we deal with the cost. But then it's sold for 50p, so again that's going to be 0.5. So then the sales then is there are 57.5 of the first rods, and they give us, remember, 5p, so that's 0.05 pounds. And then the second and the third one, uh, so so there are 424.5 add 18, and they give us a profit of 0.5. Okay, because they both sell for 50p. So the profit, so not the profit, the sales we get is 50p lots of the amount of rods we have with those two. So let's just work that out. I'll just putting all this into a calculator. And we get this. We get 224.125. I'm not going to round yet. Again, like we just did earlier, we'll round at the very end. If we need to. That's how much sales there are. Obviously, you can't have. It should be 2 digits for pence, but I'm not going to worry about that at the moment. But I'll leave it as that. So that's the sales then. Then we need the total cost, and that's the cost to make each particular rod. Let's have a look. So we are told the cost of producing a single rod is 20p. That's going to be 0.2. Um, and the first two don't have any extra cost, but when it's greater than 8.09, then we cost an extra 10p, which is obviously 0.1. So what we're going to do is, so the first two rods cost us 20p per rod. So it's going to be 0.2 lots of 57.5. Because there's 57.5 rods that are less than 7 point. I don't know what it is. And then the second lot of rods, 44.5. And then the third rod, so when it's greater than 8.09, then there's an extra. We've got cost 20p, but there's an extra 10p. So it's 0. So it's 30p in total. So it'd be 0.3, and that'd be 0.3 lots of 18. And so then the cost to be added all together would be 0.2, 57.5, add 4 to 4.5, add 0.3 of 18, would be 101.8. So therefore, the profit then is going to be the sales minus the cost. So how much we get minus how much we pay to make it. So it's 224.125 minus 101.8 will get us this number here, 122.325. And so that has been pounds then, right? It says to the nearest pound. So let's round this. Well, it's going to be 122 to the nearest pound, right? And there's your answer. So we've rounded it at the very end. There we go. That's your profit. Cool. Okay. Not too bad, actually, to be fair. I might really. Um, but then it says for part D that the same manufacturer makes metal hinges in batches. The hinges have each a probability of 0.015 having a fault. The random sample 200, so obviously that's going to be a number. Taken from each batch, and the batches accepted with fewer than 6 hinges are faulty. The manufacturer aims um, for 95% of batches to be accepted. Okay, well, we're given well, we have a probability, we have a number, and we have an x value right, of 6. I think we can compute some probabilities with that, and actually this is now going to be binomial. So we're going back to binomial because now we have a discrete, an integer amount of things, right? Trials. So the hinges are our trials, right? How many things we have. So we're going to go back to binomial. So then I'm going to say let x be b of np. So we have 200 hinges. Um, and the probability is 0.015. And that's the probability of having a fault. So x then would be the number of hinges that are faulty, right? If we define it. Oh, a bit messy. That are faulty. Okay, then we want to consider px less than or because it's 6, wasn't it? What does it say then? A random sample 200 is taken, and the batch is accepted if fewer than 6 hinges are faulty. So we want to look for how many batches are accepted, which should correspond to how many hinges. Less the probability that fewer than 6 hinges are faulty, right? So we need less than 6. That's the probability we consider. X less than 6. Again, because it's a strict inequality, it has to be less than 6. We then, because it goes in integers 1, 2, 3, 4, 5, 6. The next number down to be equal to is going to be p x less than or equal to 5, right? If we go to the next one down, because remember binomial, at least on the calculator, will only work with this specific arrangement of a probability when it's less than or equal to. Okay, let's put that in the calculator then. Okay, so let's go back to the menu. Go to 7. Then we want binomial CD variable, and then x is going to be 5. N is going to be 200, and probability is 0.015, and that's what we get 0.917. 6. Blah 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 blah. That's okay. So what's this mean? It's saying that's saying the probability that fewer than 6 what was it rods or hinges sorry are faulty is 91.76, but the manager's aim for 90 for at least 95% of them to be of batches to be correct, right? To not have enough faults. Yeah, so aim is 95% batch to be accepted. So, but we saw that only 91% of batches are accepted, which obviously corresponds to fewer than 6 hinges are faulty. So I'm going to say, therefore, 91.7 is less than 95%. Therefore, manager's aim. So what it asks us to do. Explain it's not likely to achieve the aim, right? So the manager's aim is unlikely to be achieved. There we are. Okay, not too bad of a question, really. Okay, let's move on. Sorry. Okay. Diane. Let's do part A. Diane uses the large data set to investigate the daily total rainfall for Camborne. Write down how a value of R less than or equal to 0.5 is recorded in the large data set. Um, um, well, this you need to know what the large data set is, right? But I don't think this one's too bad. Because obviously this is a very, very small number, but it's still not zero. And what we say then is, well, it's a trace, right? We just call it trace or TR, okay? Um, so that represents like a very extremely small number of rain, okay? A trace. Um, it's like, for example, with food, you might see something called like a trace of nuts or something like that. Like you can't rule out some nuts, but practically it's like 0.0. You know what I mean? Like 0.0, like 2% of that are nuts. You know. Um. So a trace. So that would just be trace. That's something you mostly need to know. But hopefully you've seen some questions with large data set, and you probably used to see this word trace. And you should recognise, even from real life, that it means like a very small number like this, right? Here. So it's recorded as trace. Um, okay. Uh, okay. Then Diane uses. Okay, I'm gonna get rid of this now. Diane uses the data for the 31 days of August. For Camborne and calculates the following statistics. We use the statistics to calculate the mean and the standard deviation. Okay. So the mean, first of all. So that's going to be X bar. You should know that's going to be the sum of the values over how many there are, which is n. But sum of X, they're giving R in this case, I guess, not R. So it'd be R, okay, not X. But it doesn't really matter. It's the same thing. So sum of R, they're giving us is 174.9 over n, which was um, 31. So that's your mean. So you can work that out with the calculator, which is 5.642 to 3 dp. Then the standard deviation, which is sigma, that's going to be uh, the square root. And I'm not sure you need to know this. Have a look in the formula book and say, but it's going to be the square root of sum of the values squared over n minus the mean squared, or I guess in particular, sum of r over n all squared, and that's all square rooted. I'm going to look at the formula book if you need to learn that or not. Let me have a look. Oh, they give you here standard deviation. Oh, it's right here. Okay. But obviously, instead of like I just said, instead of saying sum of r over n here, obviously that's just the mean. So they've just said x bar, which represents the mean. X bar is just the mean. Okay. So yeah, they give you that in the formula, but obviously you're going to need to work out the mean. You can kind of work that from GCC, really, to be honest. But yeah. But yeah, that version will help. Sometimes they do actually give you this one. For some, I've seen on some past papers that write something called SXX, and then actually work at standard deviation. So you will need to pay attention to this formula maybe, but you don't need to remember standard deviation as long as you can work with and interpret this formula in the book. Okay. But yeah. So you don't need to remember standard deviation, but you do need to work out the mean. I don't think they give you the mean. I don't think they're that nice, are they? No, but they give you an interquartile range, and that the standard deviation is the root of the variance. Interesting. Yeah, okay, that's all they give you really. Okay, cool. So yeah, so that's a standard deviation. So let's put that in the calculator. So let's plug these values in. So it's going to be the square root of sum of r squared, which is 3523 point 283 over 31. It's really wonk. I'm going to get rid of the square root here. There we are. Minus the mean squared. So that's going to be 174.9 over 31 all squared. That's from part A, the first part. So you work that all out, you will get 9.0456 to 4dp. I've rounded that up, but yeah. Okay, cool. So then it says Diane believes that the mean daily total rainfall in August is less in the south in the UK than the north. The mean daily total rainfall for Lucas is 1.72 millimeters. State whether this provides evidence of Diane's belief. So Diane's such as saying south of the UK and then the north. Obviously, north is at the top of the UK. It's saying that obviously the rainfall in the south will be less, so it's kind of sunny, I guess, which makes sense because the north is like colder in general. But does the data support it? Well, it's given Lucas and the mean there, but we've also worked out the mean for Camborne. So actually, this is also testing your large data skills knowledge. You need to know where Camborne and Lucas is. Well, I guess particularly you need to work out which is more northern of the two. And actually, again, this is something you just need to learn. I will recommend, so Mr. Bison Maths has done a really good video about large data sets and what you need to learn and how to learn it. But actually, so to learn the locations, to work out the order from north to south, well, there are five you need to learn. Camborne in the UK anyway. Camborne, Herne, Heathrow, uh, Leeming, Leeman, and Lucas. Okay. And that is uh, actually I probably should write it the other way around, but this is north to south, okay, and that's in that order. And actually, you should notice it's kind of alphabetical order. So south starts with Camborne, so that's a C, and then it goes from H to L, and obviously L E E L E U. So that's an alphabetical order, but this isn't. So you just need to remember that in general it goes in alphabetical order from south to north, except for the two H's, the Herne and Heathrow. I don't have a way of giving a better rule than that. I mean, that's what Mr. Bison did. I can't come up with a better way, at least at the moment. You can learn that rule, but you still need to learn these two. But in this particular case, we're only comparing between Camborne and Lucas. So Lucas is more north than Camborne. So I'm going to write that down. uh, Lucas, I don't know how to pronounce it, is more northern than Camborne. Okay, so what you can expect is if it's more north, it's going to have more rain. That's what Diane's saying. Um, okay, let's have a look. But we worked out Camborne. The mean was the mean was 5.642, so like 5.64, and then 5.64 was greater than 1.72. That was the mean for the Lucas, wasn't it? Here, there it is. So actually, it's saying Lucas has less rainfall. But that contradicts what she's saying. Therefore, this does not support Diane's belief. How do you spell her name? Uh, Diane. Okay, without an E. Okay, weird names at Edexcel. This is not. This is not support. Sorry, Diane's belief. Uh, okay, because obviously, like as we said, Lucas is more northern, but she's saying more northern areas have more rainfall than the southern. But Camborne and Lucas has less rainfall than Camborne, so there it doesn't support what she's saying. Uh, but yeah, that's it. So you just need to learn the location, really. Again, you can use that sort of rule of the alphabetical order to help, but really, yeah, that's too much. And then Diane uses the large data set to estimate the proportion of days with no rain in Camborne um, to 0.27. So, okay. So 27% of days have no rain. Then it says explain why the distribution B of 14, 0.27, might not be a reasonable model for the number of days without rain for 14-day summer event. Okay. Well, immediately I notice the difference here is we only have 14 days. Here, this is practically the whole year, or at least like spanning a good few months of the data set, right? So actually, immediately right away, they're not really like it, it's it's not reliable, is it? Because there's so few days. It's almost like you're extrapolating and not extrapolating, but you're kind of taking the extreme end of the data, right? Because this is a 40-day summer event. So really, the proportion is going to be a lot more in the summer in those few summer days. Like at the moment, actually, we're having a heat wave at the moment, so it's going to be less rain. But in general, there's rain. Um, so actually, because of that, it's not reasonable because the probability would not be 0.27. You're assuming the general probability would work for like this fixed, really shortened time duration, right, of 14 days. So it's not reasonable because you can't not extrapolate because it's part of it, but you can't assume it's always 0.27 for every single period in that time, you know? So that's going to be a reason. Um, so a 14-day summer event will not have will have a much higher proportion of days without rain compared to like the rest of the year, right? So I guess you could say like so greater than 0.27, which is what they assume it to be. So that's the thing. So that you didn't need a large data set for. But in general, usually there is a question about large data set. You know, a lot of it you can work out without the large data set. Like it just means and standard deviation. And the final question as well, actually. you can still get a good few marks. So just because it's talking about a large data set, don't just immediately freak out. Say, no, I'm not doing that question. You could tackle a good chunk of it and also guess it if you don't really know. For example, the months. If you're talking about like a particular month that's unusually like cold or something, maybe it's because it's in October or something like that. I don't know, but usually what I'm seeing, they're only worth at most 3 marks for specific large data set knowledge. Again, that's up to you, whether you want to spend all the time learning it, even if you watch Mr. Bison's video, it's up to you. Or you can use that marks to perfect in other areas of applied. That's up to you. I agree, absolutely sucks. I don't know why it's in the spec. I personally think it should be a 5% coursework grade where you deal with Excel and then do some stats and stuff. I don't know, but I'm not at Excel. But yeah. Anyway, question 4. A dentist knows from past records that 10% of customers arrive late to their appointment. A new manager believes there's been a change in the proportion of customers who arrive late to their appointment. A random sample of 50, so I'm going to again highlight the numbers. Sample of 50, so that's giving me the N, like how many people there are, trials or whatever. We're also told 10% were late, so I bear that in mind. Okay, so samples taken. Write down a null hypothesis corresponding to no change in the proportion of customers who arrive late. And an alternative hypothesis corresponds. So the hypothesis is the manager believes obviously there's a change in the customers that are late, the proportion, right? Okay, so this is pretty standard. So the null hypothesis is like nothing's changed, right? So then the probability. So what we're testing here is the probability, and it always, obviously, hopefully you can recognise this is going to be a binomial because you can't have because we're going to have like again an integer amount of customers, a whole like you can't have it's not continuous data, so it's not a normal, so it's be binomial. So the only thing with binomial is the testing the probability. So we're going to test the probability that the amount of people that are late is different to 10%. But if we assume nothing's changed, then actually, indeed, the probability would be 0.1. So exactly 10% of the customers are late. Then the alternative is this doesn't happen, and again, then you test the belief. So the belief is there is a change. They didn't say which way. They've not said that it's less than 10% or greater than. It said there's just a change. That means it's just not equal to 0.1. So that's for two-tailed when it's both greater than 0.1 and less than 0.1. Okay. So we say it's not equal to 0.1. Cool. So that's your alternative hypothesis. That's really it. You just write that down. Cool. Part B. Using a 5% level significance, find the critical region for a two-tailed test for the null hypothesis. In part A. So we need to find a critical region for this. So what that means is, again, assume a distribution looks like this, like a normal, but obviously it's just discrete values. But assume it looks like a normal, it doesn't really matter. So if we have some values then, like here again, what we want is if we have if how do I explain this? So what we want to find is the number of customers, what was it, like N or whatever, such that if it's unusually large or unusually small amount of customers, then there's something not right there. So how so when it's referring to significance level, draw this again. Significance level, it's referring to the probability of like, well, actually, there's something going on here. So less than 0.025%, that's 2.5%, sorry, either end. So what that means is either end, we want to find the number of customers such that this area is 2.5%, right? and on the upper end, the other tail of the curve, right? This will also be 2.5% as well. So what that is saying then is these are the critical regions, right? These areas that are shaded. And so if we find this value of x, x1 and x2, for example, these are like the boundary. If we have the number of customers that fall into it, so say this was like, I don't know, like 3 customers that are late out of 50, right? Because they have 50. If there are like 2 or 1 customers late, uh, it's quite significant, isn't it, really? Like that's a big like difference to what you expect. Whereas if you only like say like the mean, I don't know, say 10% of 50 is 5, right? Say we had like 4 customers late. That's not really a big enough difference to conclude, well, actually there is a difference. There could be a fluke, it could be one, or maybe that particular day, I don't know, there's traffic and like a few customers were there. But then if we're looking for a significant like difference either side, so when actually that there is actually, you know what I mean, there is something there. So evidence we call it. Um, and that's how we set this up, really. So that's essentially what we're saying. We want the probability. But we don't know that's 3. We just heard x1. We want to find an x. We want to find the number of customers such that uh, the probability that they're late is less than 2.5%. Right. Uh, no, sorry. The proportion of customers. Um, that 2.5%. Um, so I want to find this. So px, I'm going to jump into it anyway. So we firstly want p of x. I'm going to call this a and b actually. A and b. So firstly, at the lower end, this end, we want the number a, the amount of people a, such that it's going to be 0.025. The probability um, that A people are late is 2.5%. So obviously that's going to be a really small proportion. And so anything that's less than or equal to A, then actually there is something going on. And the 2.5% as well, you could also, that's another way of looking at that is say, well, the opposite 97.5%. If we want to say like 97.5% certainty that there is no difference. So that means if it's less than 2.5%, then you cannot say for sure that you cannot accept that nothing's changed because it's such a stark amount. You know what I mean? So 2.5%. If it's less than 2.5%, so you probably uh, you want to be like over 97.5% sure that there is a change, right? So if say we only had this value that was what 1%, then you're basically saying for like 99% certainty that there is a difference, there's a change, right? We basically want a degree of certainty to be able to accept, that something's changed, that we accept H1, and that's what we're saying essentially. That we want a number such that it gives us more than what 5% overall, so more than 95% certainty that there is a change, and that's essentially what this is doing. Anyway, I've waffled on for that. So essentially, that's your critical region. Um, and again, use a graph like this to visualize, right, what's going on. So we want the probability of that's less than 8 customers is 2.5%, that they're late. But also, I should probably say this is going to be binomially distributed then between n, which was 50, was it? And the probability they're late is also 0.1. And so, and this is a binomial. Unfortunately, unlike the normal, my calculator anyway, doesn't have an inverse version to find a given the probability. What you instead need to do is to just keep plugging in values of a until you get the first value that's less Actually, it's not equal to, it's less than. There we go. Okay. So we do have CD option. Again, let's pick like 1. Okay, let's pick 1. Then N was 50. Then we probably should 0.1. So it's 0.03. But 0.03 is bigger than 0.02. So that's not fine. Well, then the only other value is 0. And that is 0.005. So probability that x less than or equal to 1 is what was it, 0.03 something. And so then probability that x less than or equal to 0, well, that's just equal to 0, but it doesn't really matter. That's 0.005, right? That's what that's in standard form. Something. But clearly that is 0.005 is clearly less than 0.025. Therefore, A is equal to 0. Hopefully you can spot that, right? So I wrote x less than or equal to 1 to actually to show, I guess, examiner or whoever, that actually I'm testing values, and this value is above 0.025, so then I'm considering the next value down. Okay, and actually 0 is the first value that goes below 0.025, and unfortunately 0 is the only value. So that's A0, so that's the critical region. So on the lower end, we can only accept that there's a difference if there are no customers late, okay? Which I guess makes sense, right? If you're claiming that 0.1% are late, with like 97.5% certain, 95% certainty, wow, the only way you're going to be certain is that none of them are late, right? That's a huge difference. I don't know, but yeah. Then we need to look at the other end and say, well, then the probability x greater than equal to b, so this upper end here. So again, at the point where there is a lot of people late, the lower end we're looking at basically none of them are late. Now we're looking at there's lots of them late, okay? So that's going to be, again, the probability there is going to be greater than 0. Less than, sorry, 0.025. But what's the problem here? We have a greater than or equal to. We need to convert to a less than or equal to. So that's going to be probability. So then we can say, well, we can flip it around. So probability x is less than or less than b minus 1. Is greater than. Hang on. No, I'll tell you the safer way of doing this. Px less than or equal to b is the same as say 1 minus px less than or equal to b. There we go. So again, like with the normal argument, the total area under the curve has to be 1. So if I'm saying on this end, for example, oh, that's a horrible curve. If I'm saying 2.5% that side, then the other side has to be 97.5. And that's what I'm doing there, okay? And so that's going to have to, well, that's the same probability. Of 0.025. But then minus px less than b has to be less than minus, well, 0.025 minus 1 would be minus 0.975. So therefore then px less than b, if I then divide by minus 1, you flip the inequality sign, 0.975. So I want the value of b. Well, actually, what's the problem here? We need it to be less than or equal to. So that means probability x less than or equal to the next number down, so p minus 1, is greater than 0.975, okay? And then at that point, I'm going to test values with the binomial, which I'll do here. That instead give a probability that exceeds 0.975. So we're going to test the upper value of numbers for x. So let's try 20. Okay, so that 0.99 is clearly above, so let's consider the next number down. And not 21. No, next number up, down. Sorry. 18. Again, let's try 15. Okay. Again, still 0.99. We need it to go down a little bit. 12. 0.998. That's still greater than 0.97. Let's try 11. 0.996. Nope. Let's try 10. 0.9906. No. Let's try 9. 0.975. Okay, so I think it might be this, but let's just write it down. So px less than equal to 9 is 0.975. 46. But then let's verify that is indeed the first number that exceeds 0.975. But then do the next number, and hopefully that should be below. So let's try 8. 0.94. There we go. So that's less than the probability. Okay. And there we are. So therefore, what we're going to say, therefore B, and particularly B minus 1, because remember, the probability is x less than equal to B minus 1 has to exceed. So B minus 1 equals 9. So B is the critical value at the end, at the right of that tail, at the upper end. So B minus 1 is 9, therefore B is 10. Okay, and that's the upper region critical value. Okay, and I guess I'd say 0.9754 is greater than 0.975, just to kind of really cover my bases. I'll probably write it more than you need to, but I'm just really trying to explain it here. That I'm choosing the first value that goes above 0.975. Okay, so B minus 1 is 9, so B equals 10. So that's our critical region. So your critical region is obviously those two critical values. So it's going to be x then is equal to 0. Now I said less than or equal to 0. So I'm talking about this value here. But obviously the initial, not the initial, but the least value of x has to be 0. Every binomial starts like this: 1, 0, 1, 2, 3, dot dot dot, to how many trials you have. So 0 is the starting value. So really, we're just saying x is 0 instead of equal, less than or equal to. So that's the lower end. But then the upper end is x greater than or equal to 10. Okay, remember, this is our critical region at the upper tail. So x has to be greater than or equal to b. B was 10. So there we are. Okay. There we are. Okay. Part C says finding actual level of significance based on your critical region. They do like asking that, but essentially what that's saying is obviously the critical region, the significance level we defined it to be. So the amount of, like I said earlier, the amount of assurance we have. So we want to be 5%. So we're saying we want to be 95% sure or more that more than 95% sure that indeed the proportion of people late is different to 0.1 or 10%, right? But actually, what this probability is giving us exactly is so px greater than or equal to 10, for example, will give us a different probability of 0.025. So basically, the actual level of significance then is the probability, the exact probability of substituting these two endpoints in. So firstly, probability x equal to 0. With that, you can just use the PD function in your binomial. So if we go back to, I could use CD, I guess. So 0, 50, and 0.1 is this nasty number here, and it doesn't convert. So that's going to be 0.0051 53. Okay, you do need to remember standard form for this, really. So that's the probability that there are exactly 0 people late. So that's like the critical value at the lower end. Then the probability at the upper end is going to be p x greater than or equal to 10. So again, that's going to be 1 minus the probability x is less than or equal to 9. But we worked that out. So we know it's 1 minus 0.97546. We worked that out there. Okay. And then that would be, if we put equal that, uh, 0.02454, blah, blah, blah. And that would be a 2.45% significance level. Okay. I'm sorry. Hang on, but I'm going ahead of myself here. So that's saying that's the exact probability at the upper end that you would accept, the alternative. Um, so then the actual significance level is the addition of these two probabilities, right? So the probability at the lower end of the critical region and the probability of the upper critical region, that gives you the true significance that level. So I'm going to say true significance level. It's going to be these two probabilities of 0.005153 added with 0.02454, and that's going to get me 0.029693. And so as a percentage, that would give us a 2.97% significance level, and that's your true one. So actually, 5% is kind of like the minimum, but actually, we can actually be really precise. It's like with this model, the test, that actually gives us a 2.97% significance level. So that would be what, 100 minus 2.97. Would give us like a 97.3%, 0.3% level of certainty that that indeed there is a significant difference there, so we'd accept the alternative. Anyway, so that's how you compute the alternative, the actual level significance, sorry, where you calculate the probability of each critical region by clearly computing the endpoints. Okay, so probably x less than or equal to a, and probably x greater than or equal to b. Now with the b, you're going to have to do 1 minus the probability. Okay. Cool. So that gives you the actual significance level. And then it says the manager observes that 15 arrived late. Well, the critical region in part B was x greater than or equal to 10. Now 15 lies in that region, doesn't it? Because 15 is bigger than 10. So for part D, I'll do part D here. Actually, no, I won't. I'll do part D here. 15 is greater than 10, so lies in critical region. Therefore, there is enough evidence to reject H0 and therefore accept the alternative H1. So the manager's belief is correct. Well, not correct, but it's likely to be correct. So manager's belief likely to be correct. There we are. There we are. Okay. But yeah, that's the whole idea with hypothesis testing. I probably overcomplicated it a bit there. I'm not gonna lie. I do apologise. That's a bit messy. The explanation there. But all in all you're essentially doing is, well, say you're setting one probability x less than or equal to a. That's the lower tail, the lower critical region, and you want a number that gives you less than 0.025, and you want the highest one. Okay. On the upper end, you want the probability x greater than or equal to b, so the upper critical region, which is also less than 0.025 at the upper end. But then you can switch it around and say probability x less than or equal to b minus 1 is greater than 0.975, but taking one away. And that's what you're essentially doing. But yeah, okay. Question 5. A company has 1,825 employees. The employees are classified as professional, skilled, or elementary. The following table shows the number of employees in each classification and 2 areas. Okay, it's all given here. Okay, in the table. Employees chosen at random. Find the probability that the employee is skilled. I'm going to do these up here. Am I going to do it up here? Yeah, I got all the numbers here. So the probability they're skilled. So that again, so the total again is 1825. So out of those number of employees, how many are skilled? Well, it's going to be these two numbers added together, isn't it? 275 and 90. And so the total that's skilled is then if we do that calculation, 275 plus 90 over 1825 gets me a fifth. Okay. Um, Okay, cool. Part B then says lives in an area B and is not a professional. Okay, so this and is key. What that means is then because of an and, remember when Jesus said the and or rule? So if we have two or events, we add the probabilities. If we have two and, we times them. So because we want the probability the living area be and the probability they're not professional, we need to times them together. So the probability that the lives in area B is going to be these three numbers added together, right? That's how many live in area B out of 1825, and then we're timesing it by the amount that are not a professional. So it's going to be these four numbers, right? To exclude these two, right? So it's going to be 275, add 90, add 260, add 80, over 1825. We put all that into a calculator. Um, you get. I feel like I overcomplicated it here, but let's see what this boils down to. Yeah, that's not. Yeah, that's not right. Apologies. Yeah, I overcomplicated it. Yes, because you know why that's wrong. That is wrong. Do you know why? Because these are not necessarily independent from each other. When you apply that rule of two events times them together, you can only do that when they're independent. In GCSE, that's an assumption. That's why you know why? Because there's a lot of GCSE streams recently as well, and you're just used to doing this when you see an and. But I should be a bit more critical than that. No, that's wrong because obviously you had to account for the intersection. So we don't know they're independent, so we can't just times the probabilities. My mistake there. What you do then want to do is account how many are in both. So area B and not a professional, and that's why I've complicated it. So lives in area B is here, and not a professional. It's going to be these two values here. So we're only interested in 90 and 80 over the total, and there we are. Okay, there we go. That's a good learning curve. That's a good what you know what I mean. I think that's a good uh pitfall to explain. I think of why you can't do that. And why independence is an important concept in probability. Anyway, so you get this number 34 over 365. There we go. And so that method, this worked because I'm accounting for the intersections. See how I did here, B, and then I've looked at the intersection by doing this. So I've accounted for the fact there might not be independent there. Anyway, so that's part B. Then we are given, oh God, we're given a big block of text. I'm not going to read all that out. I'm going to then see, well, using this information, complete the Venn diagram on the opposite page. Oh, okay, they've given us some numbers already. So H, R, and F. What is H, R, and F? Let's have a look. Uh, Here, event F is the employees in a professional. Event H is an employee that works from home, and event R that employs from area A. Be given information about employees that work from home. Okay. Okay, so we need to fill this in with a Venn diagram. So the way it even teaches you to see, but it's, also this, well, not teach, but when I went over the papers, um, you need to work from the intersections first, and then work your way out. Okay. So here I work with the triple intersection, then I'll do the double intersection, and then I do the single, and then I'll try work, on the outside last if I can. So we first we're interested in the triple one. So how many are in all three groups? So we want an employee that's a professional, works from home, and is from area A. Well, we could work out using them from the table. How many are professional and from area A? Right, it's exactly this number here. But then we need to work how many are what's it called? How many also work from home? So let's have a look at this. 65% of professional employees in both Area A and Area B work from home. 40% of skilled employees in both Area A and Area B work from home, and 50% elementary in both of them work from home. Okay. Uh, right. Okay. 65% professional employees in both Area A and Area B. Right. Okay. Um. They don't split it up though between A and B exactly, do they? Uh, well, let's work. These are numbers we can compute actually. So 65% of professional employees work from home. But we know the total here. So if I do, let me get rid of this now. If I do a total here of these three, I can then work out the proportion that I work from home from each category. So no, but then I'm going to need to work out how many from area A work from home. Because this gives me area A and B, but I want to work out area A and B separately that work from home to work out the intersection. Um, I guess the assumption is you can split them up. Yeah, it's both. So I guess you could say you could do 65% of each of them individually, I think, rather than adding them and then do 65%. I think that's the way to do it, but the question isn't that clear. I don't know. I think that's the way to do it. I think because then you work out how many are in city in town A, for example, in area A, is professional and works from home, which is what we want. Okay, I think. So let's work that out. So then we want. How should I write this? So I'm going to bear these in mind first of all: 65%, 40%, 5%. Where do I write the data? Now I'll tell you what. I'm going to extend the table. Probably messy. I'm going to say A home and B home, and that represents how many from A that are professional, that unskilled, elementary, and respectively that work from home. It's an awful table. Oh my god. There we go. It's a little bit better. So firstly, 740. That's 65% of that is going to be 0.65 times 740. That's going to get me 481. Likewise, B that works from home is 380 times 0.65 gives us 247. Uh, and then again, skilled, now it's 40% here. So 0.4 times 275 is 110. Then 90 times 0.4 is 36. Then 260 times, and then the probability here for elementary is 5%. So 0.05 will give me 13. And then 0.05 times 80 will give me 4. There we go. Uh, cool. So now we've got we broke it down to include working from home. Okay. So then the triple intersection then to H, R, and F. So those that are professional, work from home, and from area A. That's just going to be, I don't even want to circle it, but it's going to be the number there, isn't it? You know, the 481. That's representing professional here. That is from area A and works from home. So the intersection is just going to be 481. The triple intersection here. Cool. Now we're going to work out this this double intersection between F and R. So F and R, so employee that's professional, that is from area A. So that's just going to be this number here. Professional area A is 740. But we also need to account for the fact we already have 481 that are from area A and are professional, but also work from home. So we need to subtract that from 481. So we're going to have 740 take away 481 to give us 259. And I guess specifically, this number is the people that are professional from area A that do not work from home. Because if they did work from home, then it would be included in the triple intersection. So then that makes sense because then we add these two together, you get the people, irrespective if they work from home or not, that they are just simply from area A and are professional. Okay, now we just got this single intersection here, which is H. Um, so H is the employee that works from home. Okay, well, that we're just going to add all these numbers together, aren't we? These two tables together. Um, so I'm going to say works from home. The total then is going to be 481, add 247, add 110, add 36, add 13, add 4. Does it not? Oh, it doesn't tell you. Does it have any work from home numerically? No, we have to work it out. Okay, so we do all that. So we add the other six numbers. 481, add 247, add 110, add 36, add 13, add 4. Gets me 891. Okay. Um, but we do not put 891 here because we then need to account for all the other numbers as well. Okay, that 891 only tells us that all the numbers in the circle in total add up to 891. But when we just want this single part here away from all the intersections, we're going to do 891, take away the other three parts here. So 123 here, the 481 and the 247. These are also numbers in the circle H. So we take that away, we get exclusively just H. So take away 123, take away 481, take away 247. you're left with at 40. And that should be in there. Cool. But we're not finished yet because we need to write a number outside the box. And the number, and in general, everything inside the box has to account for every single employee. Because, there are employees that don't belong to groups H, R, and F. So employees that neither are professional, work from home, or from area A. Okay, there are still employees that exist outside of those circles. So in total, there are 1825. So to work that the total outside the box is going to be 1825. Take away all the numbers inside the circles. So 1825 minus 40. Take away 123. Take away 412. Take away 247. Take away 481. Take away 259. Take away 133. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. There's 7 numbers. Okay, that should be right. So 1825, take away 14, take away 123, take away 412, take away 247, take away 481, take away 259, take away 133, there we go, 130. And that's outside the box, and there we go, we complete the Venn diagram. Okay, cool. Then it says, using this information, complete the Venn diagram. Oh, we did that. Then we need to find these 3 probabilities. So you just need to work out what they're saying. So first of all, we have these shapes and this weird um, rainbow arc shape and the reverse. It looks like parabolas, right, of the quadratic. So that's here. So what this means, and that means and. Okay, and like I say with the GC3 people, it looks like an N in a way, doesn't it? And has an N shape, and has like a N shape, and as an as an N sound. So you can remember the N as an and, but hopefully you're used to seeing that symbol by now. What it means. On the flip side, U means or, and I guess it also has like a U shape as well, or like a U, like vaguely. I don't know if that helps you remember it. Then yeah, that's how I remember it. But anyway, so that means and. So we need the events R dash and F. Now dash means not in R. So this is saying the regions that are not in R and in F. Okay, so if we look at a Venn diagram, so not in R, we can exclude this whole circle here, and we're going to be left with this number, this number, this number, and this number, right? That's not in the circle R, but we also need it to be in F. Now, what numbers left are in F? Well, it's these. If you take away these two, it's the remaining two circled, isn't it? So those are numbers that are in F and not in R. So then our probability then, if I do, what is it, part D? Probability R dash and F. That's just simply going to be then 247 add 133 out of the total of 1825, was it? Yes. And then compute that, you get 76 over 365. Cool. So then part E is saying, then we get rid of this now, the circle bit. Then it's now saying probability, okay, of H or R dash. So it's saying F inside the bracket, not. Okay. What's inside the bracket though? H or R. Okay. The U again, the or the U. H or R. So if the circle, so the numbers are in the circles H or R. So it's going to be this number, this number, this number, this number, this number, this and this number. Those are the numbers that are in H or R, right? Uh, but then we are saying we want then all of that is to a dash, which means we do not want anything inside here. So we do not want any of those numbers, and we want the other numbers instead. So it's actually going to be these two numbers remaining, right? So if we get rid of these circles again, instead we want these two numbers that we circled. So the probability of uh, R or H dash, it's going to be 133 add 130 over 1825. And so put that into a calculator. It's 263 over 1825. And there we are. Okay, then part F, final one. Find F, that line, vertical line is given. So F given H. So what that is saying is, given is a conditional probability. So we add a condition on, which is H has to occur. So F given H. So given H, first of all, that means we have to consider all the numbers are only in H, which means this number, everything in the H circle. So it's these four numbers here, right? So that's our total now. So immediately our total is going to be all the numbers that are already in H. So given H is true, essentially. So H occurs. So that out the total now is just going to be in H, which is going to be 14. Add 123. Add 481. Add 247. Okay, so that's out of H, given H, but then we need F. So from these numbers that are circled, how many are also in F? And actually, then if we, it's going to be these two numbers left, right? These are overlapping with F. Okay, so then so the thing we want is then 481. Add 247. And so then, if you work that out, 40 and 123. You get this number here, 728 over 891, and that's your probability. Cool. I quite like that question actually. I don't know. I can see people struggling maybe, but I don't know. I like that question really. Probably in an exam, I'm sure you'll probably hate it though. But yeah, there we are. Nice. Okay. And they do like asking those sort of Venn diagram questions as well. So if you can wrap your head around them, you know, they're not nice marks. They're nice marks to pick up. Anyway, final question. Anna is invested. I think, and by the way, I'll talk about this later after. But I'm thinking of doing mechanics tomorrow because we're running out of time here. But I'll make sure to upload that first thing whenever I get time to do it tomorrow. Anyway, so final question. Anna is investigating the relationship between exercise and resting heart rate. She takes a sample of 19. Again, I'm going to highlight the number, underline it, sample of 19 people. The records their resting heart rate H and the number of minutes spent exercising, which is M. And the results from the scattering diagram. Interpret the nature relationship between H and M. So it wants you to comment on the relationship between H and M. But obviously that's going to be a negative correlation. As one variable goes up, the other variable goes down. So it's a negative correlation. But they want you to explain what that means using the variables H and M. So that's going to be, if I write this down in words. Oh, I don't know. Okay. I'll write it here. So what that's saying is there is a negative correlation between M and H. But what is H and M or M and H? So that's saying as the resting heart rate uh, uh, increases, so as that goes up, obviously that's going down the M, but M is the number of minutes. Exercising each week decreases. Okay, I guess that makes sense in real life as well because you have a high heart rate, so it's a bit unhealthier. If you'd spent less time exercising. But yeah, so that's what it means. Interpret. Interpret means uh, don't just say it's a negative correlation between H and M. You need to say what does that mean exactly. So what is H and M? So H is the resting heart rate, and M is the number of minutes spent exercising. And so you're saying as one decreases, the other increases, and vice versa. Um, so you don't just say there's a negative correlation, or you don't just say H and M. You have to explicitly be very explicit, and write out what that means, what they've given here. Okay. Yeah, that's what I think. That should be what they're after. Um, okay. Part B. Then we said Anna codes the data using the formula X and Y is log 10 of each. The PMCC between X and Y is this here. Test whether or not there's a significant evidence of a negative correlation between X and Y. You should state your hypothesis clearly, sorry. Use the 5 significance level and you state the critical value used. So again, that's exactly a sort of similar concept. So we need some sort of data, test statistic. So again, kind of look at this. So again, say if, oh, that's not really centered well. It should be centered here. Okay, say this is our R value, right? Uh, uh, we need to find a critical region for R, okay? Such that if say R then lies in 0.87897, uh, then it lies in the critical region. So that means there is enough evidence to reject the null hypothesis and accept the alternative. But we need to find this critical value, this R critical value. So I'm going to call it R, I don't know, big R, I guess. Um, so this is sort of like a graph of the PMCC values, right? So we need to find the critical value of the critical PMCC R, such that anything less than that will be enough evidence. So there's a strong negative correlation. Remember, this is saying negative 0.897. If it's close to 0.1, 0.1 means it's a completely negative correlation. So if it's 0.89, so it's still very, very strong negative correlation. Okay, that's what that's saying. So we need it to be negative enough to lie in a critical region. Therefore, we can accept the alternative hypothesis. Anyway, so enough waffle. Let me charge my. There we are. We need to find this sort of critical region. That's not really what they use, but they talk about critical values. There we are. So, okay, how are we going to find that? Right, it's actually really simple with PMCC. We don't need to compute any probabilities. We just need to use the table and the stats book. So what we need is the value of n, which is 17, I believe. We highlighted up there. Yeah, 19 people, sorry. What we also need is the significance level, which is p. Well, that's 5%, so that's going to be 0.05. And that's what we need. That will give us then the critical value of the PMCC if we then use the data table. So that's going to be at the very back probably. Let's have a look. Oh, here we are, right on the right page. So again, it's done by sample size. So we're going to need to look for 19, which is here. Then we need to read off these values here, right? That's very, very badly circled. Then we need a significance level here, so the significance level of 0.05. So that is actually going to be this number here. That is your critical region of 0.387887. But what you're going to notice is that they're all positive. But here we're dealing with negative. So really we just need to flip it because this data table is assuming a positive correlation. But obviously, a positive would be greater than 0. But in this case, we're working with a negative correlation, so we need to flip the sign to be minus. So our critical value, I'm going to say from data table, and that's probably the only time you're going to need to reference the value table, because the calculator do everything else with relating to binomial and normal. But anyway, the critical value is minus 0.3887, was it? Let me go back. Yeah, so it was 3.887, but then we need to make it negative. There we are. So that's our critical value, right? So again, that means any what's it called? Any PMCC value less than that will be in the critical region. Well, actually, it is. So minus 0.897 is actually less than minus 0.3887. Therefore, I need to set my hypothesis. Oh God! So the hypothesis is our critical value. What did I say? R. Technically, they want row. This little weird P that's a bit slanted. Okay. There. I don't know. It's not slanted enough. I forget it. P. Well, what you're assuming is there is no correlation whatsoever. So there's 0, and then you're assuming alternatively there is a negative correlation. So it has to be strictly less than 0. Sorry, I should have stated it there. I didn't read the question. So set that's our hypothesis. It will always, well, it won't always be the same, but it's the same sort of method. If it says to test for a correlation, then it has to be not equal to 0. But I'm not sure they do that. Well, then I guess you halve the, yeah, I guess you could halve the significance level, and then find the up and the low. Anyway, but I assume it's normally a one-tailed test. So if it's negative, it has to be less than 0, obviously, and then positive, it has to be above 0. And I should say as well, the PMCC, obviously, as I've explained before, it gives a numerical answer for how strong the relationship is, how strong the correlation is. So if it's -1, it's it's entirely negative. So there's no doubt about it. Like it completely goes down negatively. If one goes up, the other one goes down, and vice versa. Um, so if you have like a number line here, 0 and -1, then anything in between will still be a negative. But the further along you go towards 0, it's a weaker negative correlation. Likewise here, then we go to positive one. Positive one would be an entirely positive correlation. And then obviously, again, as it goes to 0, like neutral, I guess if you wish, again, it's a weakest positive. Anyway, but that guides us with how you formulate your hypothesis. So if it's a negative correlation, it'll be less than 0. And so we want the critical value then to be such that we want strong enough PMCC values such that we then have enough evidence to reject the null hypothesis. And we do in this case. Therefore, we have enough evidence, or there is enough evidence, to reject H0, the null, right? Therefore, accept the alternative h1. Okay, there we are. So that's only 3 marks. I don't expect a lot there. Um, and so what that means is that set h1, therefore, in context, I guess that means there is enough evidence to suggest a negative correlation, right? Because that's what we're suggesting. Okay. Between x and y, yes, because we're not because it's not h and m anymore. It's x and y here. Okay. Cool. So hopefully you sort the notes by now as well. The whole test. I think a lot of people also struggle. Well, unless you memorize it. But I haven't memorized the methods really. I just with how you test significance level, test, hypothesis testing. This sort of analogy with the critical regions works all the time. It works with normal testing as well. It's the whole principle. Um, so I think that really does help to explain it. And now I've just butchered it. Um, I deleted the drawing and I didn't want to. But that's the whole sort of idea, right? You find a critical region, so the values of the critical values, and anything less than that forms our critical region, which makes sense because that's an extreme value. So if it's extreme enough, then that gives us enough. Well, actually, there's something bad going on here. So there's something going on. So we have enough evidence there. Um, yeah, it's the whole idea every single time. You find a critical value, and then it has to be less than that to form a critical region, or above if it's one or two tailed. But yeah. Okay, the final part of the question. The equation of line of best fit on y and x is this. Find an equation of the line that use the equation of the line of best fit to find the model for h. So what's going on here is we're going from y to x, and then it's asking us to use that to go from h to m. Okay, well, first of all, let's work with that. So part C, y is minus 0.05x as 1.92. Then let's substitute y in and an x in. So y's log 10 of h is equal to minus 0.05 log 10 of m add 1.92. Okay, but now we've got h and m's, now we just need to rearrange to this. And we're going to use our logarithms, right? And I think the best way to do this is to bring all the logs together. So it's kind of like solving the log equation in a way. So log 10 of h add 0.05 log 10 of m is equal to 1.92. But we can't bring the logs together just yet because we have this coefficient in the front. So to do that, we're going to say log 10 of h. Then we're going to bring it in as a power. Remember the log rule. That log a to the n is n log a. So we're kind of doing it in reverse this time. We're using this to jump to here. Anyway, so that'd be log 10 of m to the 0.05 equals 1.92. Now we can bring them together. So therefore, then we could say that log 10 of, and then if we're bringing them together, we add two different logs, bringing them together into times inside. So it's hm to 0.05 is equal to 1.92. And then we can undo the log because then we can kind of erase everything by 10. No, that's I'm always weird. I need to be a bit more specific. That's not the right phrasing. I'm going to bring 10 and make these both powers, I guess. So then we'll say 10 to the log 10 of that is 10 to the 1.92. But the 10 will cancel the log 10. Again, you can either recognize because the inverses or because of this log rule, which is actually in the formula book, actually. I'll go over the formula book version. But you really should remember it. to be honest, because it's very, very helpful with logs, even from pure. This one here, e to the x ln a, but obviously we can generalize it to any base of a. But let's say e to the x ln a, x ln a, that's the same as e to the ln a to the x. That's saying that's equal to a to the x. So actually this cancels, okay? That's if you use a formula book. But in general, uh, a to the log of any base, I'm just going to say log of x. No, a to the x, sorry. Any base, if we change the a as well. If the same base in the log and, the base here, that's always just x, okay? Because they cancel in a sort of way. Anyway, it's a lot of waffle maybe. Hopefully you are aware of that. But then we can then cancel well, so we'll just say h n to the 0.05 is 10 to the 1.92. And now we're a lot closer, aren't we? Okay, now we just need h on its own. H equals am to the k. Well, we're going to need to get rid of the m, aren't we? So therefore, h is 10 to the 1.92 over m to the 0.05. Well, actually, we don't want to divide, but we can just bring the m on front by taking the reciprocal. So it's going to be 10 to the 1.92, lots of m to the minus 0.05, right? And so that becomes h is uh, m. What did it say? am to the k. Well, there we are. That's our equation. H is in the form of am to the k, where a is 10 to the 1.92, which is, and they want us to find it as well. So 10 to the 1.92, I guess to round it would be 83. 0.176, or I guess 18 to 2 dp, and k is minus 0.05. And there we are. So if we get rid of the brackets, I guess that's what we've got there. Okay, and there we are. That's our model. 5 marks as well, quite nice. I actually do think they're going to ask a question like that, just because there wasn't too many logs in the paper. Firstly, in both the paper you sat, but also I did talk about this at the start, but also the sort of the other paper that I think it was people with access needs who needed like a special type of paper for various difficulties. On their paper as well, there wasn't a lot of logs either. So either way, for the examples, I'm anticipating to use more logs in the stats paper. So they might ask a question like this, which is actually quite nice, really. Nice 5 marker. Don't need any stats knowledge. Yeah, there we are. Cool, and that's it. Yeah. So like I said, yeah, so like I said just a few minutes ago, I don't have time to do the mechanics section, but I will do that when I can get round to it tomorrow, in the morning or whatever, and I'll try and upload that. I'm also going to have to upload this, but I'm also going to have to cut some stuff out because there's a big pause in certain places. That I just want people sitting there for like half an hour, at a blank screen. But anyway, so I'm going to put this on the YouTube. So at the time, it's about 11 o'clock now. So hopefully I'll get that done for the night, for tomorrow morning. Then tomorrow morning or whatever, then I'll do the mechanics part. I'm also then going to do a different past paper as well. If I was hopefully should have time. I'm thinking of, I think stats 2023, maybe. I think. I'm trying to look for a paper that's a bit different. 'Cause I'm not going to lie, a lot of the applied papers, they're all the same, especially mechanics. It's the same sort of questions every time. So I'm still trying to find a bit of a different paper. But so I'm thinking 2023 stats and 2021 mechanics, because I think they're a bit different to 2022. Um, but yeah, I guess we want to practice that. I think I'll be going for those papers tomorrow. And I'll make sure to do that as well. tomorrow as well to give you enough resources. And to be fair, I think those two papers should be enough help preparation actually for Thursday. But yeah, we'll talk more about that next time. But anyway, I'm going to leave that there then now. But yeah,